All right, in this lesson, we're going to solve some complicated problems with something called free body diagrams. It is quite challenging to understand at first because there's a lot of steps, so be patient with yourself. In the end, you'll find that it's actually easier than it appears at first. So, there are 3 steps when you're trying to solve a problem with free body diagrams. First, you got to draw the free body diagram. You need to draw the forces present in a word problem. So when I give you a word problem, you have to figure out, is there gravity acting on this object? Is there friction? Is the object experiencing air resistance? Is there a normal force? You have to think through all the forces we've talked about and figure out if those forces are acting on the object. The second objective, so to speak, would be to write the net force equations, and we'll learn how to do that here today too. Write the net force equations. For said word problem. So based on the forces acting on the object, we're going to write the net force equations. We're going to write this sum of the forces. That's what the net force is. And 3, we're going to make substitutions until the equation or equations are solvable. Make substitutions until the equation or equations is or are solvable. Okay. When you're doing these substitutions, there is a group of equations that I like to refer to as the mini equations. They're the equations that consist of 3 letters or 3 variables. For example, Fg equals mg. Force of gravity equals mass times 9.8. A good one to memorize, it'll make things faster. Also, let's look at a very common one will be friction. F sub k equals mu sub k F sub n. It's our second mini equation. We won't use static friction often, so I'm not going to write it in here. 2 others will be new ones, actually. So we have this equation where it's sigma F equals ma, but what we're going to have to do with these equations is separate the horizontal from the vertical. Sigma Fx equals max. Now what that means is when you have an object, when you have forces acting on an object, some of them are horizontal, some of them are vertical. The sum of the horizontal forces will cause a horizontal acceleration. And likewise, the sum of the vertical forces will cause a vertical acceleration. And that's the gist. Those are the mini equations. I feel like I'm missing one. I might add one more later. The mini equations. So that's what step 3 is about. We're making substitutions until the equation is solvable. We're substituting in the many equations until our net force equations are solvable. So here's a very theoretical example. Instead, okay, here's a very theoretical example of what net force equations are. We're going to go with actually the most simple one. Okay, use net force equations. To calculate the normal force acting on a 0.45 kilogram coffee cup. Now, use net force equations to calculate the normal force acting on a 0.45 kilogram coffee cup. What we learned last week is that usually normal force is equal to gravity. So the net force acting on this coffee cup is going to be 0.45 times 9.8. That's the gravitational force acting on the coffee cup. So it should probably be the net force acting on the coffee cup. But we're going to prove that with these more complex net force equations. And although the net force equations aren't useful in this particular problem, it will help demonstrate how to use them. It's such an easy example. So what's step one? Well, step one when you're using net force equations and free body diagrams, we're going to draw the free body diagram. Draw the forces present in this word problem. So think about a coffee cup resting on a table. Is there friction? No, it's not sliding anywhere. Is there air resistance? No, it's not even moving. Is there gravity? Duh, gravity pulls on everything. So the coffee cup is experiencing a downward gravitational force. Very important that I draw it downward because it'll make our net force equations more correct. So why isn't the coffee cup moving? There's a normal force balancing it out. I expect you to be able to draw this on your own based on the fact that the coffee cup is sitting on a table. You should know that gravity is pulling down, normal force is pushing up, and there's no other forces. That concludes step one in solving this problem. We've drawn the forces present. Now, we need to write the net force equations for this word problem. So here's what a net force equation is. It's the sum of the forces. I'm going to look at the y direction first. What are the y forces? Well, we have Fn, we have Fg. What's the sum of those two? It's Fn plus Fg, but since Fg is down, it's negative. So Fn plus negative Fg, which is the same as just subtracting Fg. So this is what we call the net force equation. Don't get discouraged if I lose you here. We'll get used to these. They'll get easy as we go on. What about the x direction? What's the net force equation for the x direction? Well, there's no x forces, so sigma fx is 0. Okay, if I lost you there, don't worry too much about it. Look at the third step. I bet you can do the third step. Make substitutions until the equation is solvable. So, what substitutions can I make? Sigma Fy. Sigma Fy. Is there another way to represent that? Yes, it is right here. Sigma Fy is the same as May. So I'm going to make that substitution here. Fn, I can't substitute anything in for Fn, so I'll leave it as it is. What about Fg? Could I represent that in another way? Look at that. Fg equals mg. So I'll plug in mg. Why do we do that? Why do we plug in those letters? Here's why. The original is unsolvable. I don't know what the sum of the forces is. and I don't know what Fg is. I do, however, know that the mass of the coffee cup is 0.45. I know that the acceleration of the coffee cup is 0 because it's not moving. Fn stays because that's what I'm trying to solve. Going on, I know that m is 0.45, and I know that g is 9.8. So now I have something that's solvable. The original equation was not solvable, but substituting these in has provided me with a solvable equation in the sense that there's only one letter remaining. So 0 equals Fn minus, there's that same thing I typed in my calculator at the beginning. So here's a roundabout way of showing that Fn is in fact 4.41. I add 4.41 to both sides, and I get this. 4.41 equals Fn. So that's my answer. Quite confusing, I know, but let's go over what we just did. In this problem, we identified the two forces. We knew that gravity is pulling down on the coffee cup. The surface is pushing up with a normal force. So that's step one, labeling the forces. Step two, we wrote the net force equations in a summative way, meaning it's additive or subtractive. And then we plugged in our mini equations until it's solvable. Let's look at something a little more complex. Okay. Let's look at a skydiver. Calculate the acceleration of a 55 kilogram skydiver in the presence of 300 newtons of air resistance. Okay. We're going to solve this with a free body diagram. So step one is to draw the forces present in this free body diagram. So think about a skydiver falling. Are they resting on a surface? No, so there's no normal force. Are they sliding on a surface? No, so there's no friction. Are they on a planet? Yeah, that's why they're falling. So there must be a gravitational force pulling down. We also have right here that there's air resistance. And as your notes say, air resistance is always in the opposite direction of motion. So air resistance will push up on this skydiver, F sub AIR. And those are all the forces. I guess one more force would be the applied force. No one is directly pushing or pulling this skydiver. The only two things are gravity pulling down and air pushing up. It might be wise to have your list of forces with you in order to go through the list and figure out what's there and what's not there. Anyway, that's step one. We've got all the forces. What's step two? Step two is to write the net force equations. So let's do X first. What's the sum of the sideways forces? Well, there are no sideways forces, so sigma Fx is 0. What's the sum of the vertical forces? Well, the vertical forces are F air and Fg. The sum of these forces would be F air plus negative Fg, or just F air minus Fg, because subtraction is the same as adding a negative. What are we trying to calculate? We're trying to calculate acceleration. I don't see acceleration in this equation, so it looks like I need to do step 3. I've got to make substitutions until this equation is solvable. So let's look at our mini equations. It looks like, hey, look at that. There's acceleration, and I have sigma Fy in my equation here. So sigma Fy, we'll write MAY. F air, well, there's no equation for air resistance, so I'll just leave it as F air. Also, look at that. That's the air resistance. Did they give me the weight of the skydiver? No, but they gave me mass. Let's look at the mini equations. For Fg, I'll plug in mg. So basically, once you get to this step, you look at your mini equations, you plug them all in. Okay. The mass of the skydiver is going to be 55. Now you might say that A is negative 9.8, but no, not really. When there's air resistance, A is not negative 9.8. F air was given as 300. M will be 55 again. And G is 9.8. So on the right-hand side, we can type that into our calculator all at once, and we'll get negative 239. I'm skeptical about that, so I'd like to retype it. 300 minus 55 times 9.8. You can write it just like this. Negative 239. We're left with 55 AY over here. We'll divide both sides by 55. So AY will be negative 4.345. So normally, this falling object would have an acceleration of negative 9.8. However, the presence of air resistance has slowed us down, and the use of the net force equation helps us solve that quite easily. Let's take a look at one more, and we'll stop for the day. Okay. As it reaches the top of an elevator shaft, an elevator experiences a downward acceleration. Ooh, that's messy. An elevator experiences a downward acceleration of negative 0.8 meters per second squared. Calculate the normal force. Acting on a 62 kilogram rider during this slowdown. As it reaches the top of an elevator shaft, an elevator experiences a downward acceleration of negative 0.8 meters per second squared. Calculate the normal force acting on a 62 kilogram rider during this slowdown. So if you're riding in an elevator, are you experiencing gravity? Yeah. You're not going to float to the top of the elevator. You're not going to float around inside the elevator. But what's pushing you upwards? What's causing you to move up? Not gravity. It is the floor of the elevator. So this diagram is the 62 kilogram passenger. Gravity pulls down on the passenger, and normal force pushes up on the passenger. Is this person experiencing friction? Nope, they're not sliding sideways in the elevator. Are they experiencing air resistance? No, way too slow to experience any air resistance. And there's no one directly pushing on the passenger, so there's no applied force either. Here's the list of them. I mean, it might be good to have somewhere. Applied, normal, gravity. These are the types of forces. Applied force, normal force, gravitational force, friction, air resistance. You can write this down if you wish. But there's the list. Those are the main ones. I don't think I skipped any. Tension, but we won't use tension here. All right. Without even saying it, I did step one. Step one is to draw the forces present in this word problem, the forces acting on the person. Step two is to write the net force equations. Well, let's do that. What's the sum of the x forces? There are no x forces, dude. So nothing minus nothing is nothing. What about the y direction for this problem? Well, we have a vertical force of Fn and a vertical force of Fg. So it's Fn minus Fg. It's the sum of our vertical forces. Step three, make substitutions until the equation is solvable. So we'll plug in our mini equations. Remember, we're trying to get Fn. I don't know the sum of the y forces. We got to be careful on this one. So sigma Fy, we replace that with MAY. Fg, we replace that with Mg. So keep this somewhere. Keep this present. Keep this ready to go. Okay. Let's plug in everything we've got. Mass is 62. I'm going to leave AY for a moment. Fn is what we're looking for. M is 62. And G is 9.8. Remember, on that first normal force problem, the coffee cup sitting on the table, acceleration was 0 because the coffee cup is experiencing no acceleration. The coffee cup is neither speeding up nor slowing down. But here, at the top of the elevator, you're going to slow down. So you're going to experience negative 0.8 meters per second squared of acceleration. So, and this is one of those rare cases where Fn is not the same as gravity. Watch when we multiply. I got my numbers somewhere here. And I'll just multiply them again. Okay, here we go. 62 times negative 0.8. That'll be negative 49.6. 62 times 9.8 is 607.6. The whole point of this problem is I just wanted to show you that sometimes normal force is not the same as gravity. And this is the case in this problem because of the acceleration. Right here, 607.6, this is FG. 62 times 9.8, that's FG. But when I solve for Fn here, when I add 607.6 to both sides, I'll find that Fn is less than 607.6. It'll be 558 newtons. So, if there is vertical acceleration, normal force is not the same as gravity, but we'll very rarely talk about things accelerating in an elevator. And that's about it. This is a very challenging topic. Don't be overwhelmed by it. We're going to do part 2 of this tomorrow, and it'll become a little more clear as we go on. This is the only subject that we're doing this week, so don't get overwhelmed. We'll take it one day at a time. You will be an expert by the end of all this. Thanks for watching. Thanks for your patience. I'll talk to y'all soon.